Yes, as we know that we are welcome back, and then we are going to continue with applications of machine learning in crop production, revisited with practical demonstration in Weka. We've been on this for a couple of times, and then we are going to continue. So as we know that agriculture, especially food production, is very, very important, and we cannot afford to play with it. So we dedicated all these series to our farmers who have been working hard towards seeing that the world is able to feed itself. And as a way of our own little contribution towards the highly important food production. Hopefully, we have the opportunity to also visit animal production sooner or later. Meanwhile, something that is unique is why we are talking about. Of course, we know today a lot of people are going to agriculture, even professors, people from other areas of specialization. Everybody is realizing the importance of farming. So we are all going to gain one or two things. However, the most unique importance of this gathering, because somebody might ask, I'm not a farmer, I'm not in crop production. So how am I going to gain from it? No, the idea is generic. The solution being provided by machine learning or AI is generic. Once you understand how it can be used for one area, then you can easily use it for your own area of interest. You can easily use it for your own area of interest. So this is it. So the solution is generic. If it works for crop production, definitely it will work for other areas, like in engineering, like in sciences, like even in education. So I want to have an idea of, okay, how can we improve mathematics teaching in some secondary school targeted in a particular state? We can use data-driven decision-making to enhance the capacity and the capability of being able to prevent failure and other aims and objectives of educational-oriented systems. So that is why, irrespective of your field of specialization, you have a lot to gain by we looking together into how can we use machine learning in crop production. And we've discussed the theoretical basis long ago, the importance of agriculture, and then we look into the machine learning modeling process, which is an iterative process where you gather your data, you have the algorithm that you do the modeling, you have that luxury of going back. It's an iterative process. When we say something is iterative, you don't have to get it right at the first time or as the first instant. There's always room for you to go back, do hyperparameter optimization. Is the performance okay? Keep checking it, go back. Sometimes you may have to change the algorithm in going back to modeling. Change the algorithm, maybe that one is not working. And it's always good to follow the best practice in data analysis, which is start from simple algorithm and move towards complex algorithm as you struggle to get your desired outcome. Don't jump to the best algorithm in code. There's no algorithm that is best. Based on the principle of let the data speak, there is no algorithm that is best. When somebody tells you the best algorithm in machine learning is this, he doesn't understand the concept of machine learning very well. But there's no algorithm that is best in all situations. It depends on the data that you are modeling. It depends on the data that you are modeling. So you have to change the algorithm and keep changing it until you get the one that works for you. Sometimes after changing the algorithm, playing with several ones, you may not get what you are looking for. You may have to go back to possibly feature engineering, try to manipulate the features, create more features from one feature, add two features together to make one, trying to see how can this data speak clearly to me so that we can get the insight that are embedded in the data set. Sometimes you may have to go back altogether to data preparation. Maybe your data was not properly collected. Maybe you actually collected wrong information that are not very relevant to the attribute that you want to estimate or that you are looking into. So we discussed this. And this is what we are always going to be referring to. In anywhere you want to implement machine learning, the iteratory process is very, very important. So we then made a case for predictive machine learning solution in crop production. So we say predictive solution for crop production. So case which involve leveraging data-driven insight to optimize farming practices and enhance yield. The most important in agriculture is we want to enhance the yield of in crop production. So agriculture faces challenges such as unpredictable weather conditions, pest outbreaks, the need for efficient resource management, and a host of other challenges. However, a predictive solution for crop production using AI and machine learning aims to address these challenges by analyzing historical and real-time data to make informed decisions about planting. We want to see, okay, when should we plant? Is it now or when? So this decision may not be easily made, may not be easy by just looking at the data physically, but with the hindsight of a predictive solution, you may be able to tell us that based on experience from a previous data, you have historical data, so much huge data that we can take advantage of. And this data is just wasting away. So why not take advantage of it to use data-driven decision making? And then also in irrigation, you want to know, is irrigation going to work in this area or not? That is the irrigation going to work or irrigation is not going to work? You can take those decisions based on data-driven system. What of pest control? We know how pests can invade suddenly a huge farm and render the entire effort wasted. With data-driven decision-making, we can prevent it. I call it proactive decision-making. We don't need to wait for trouble to strike, for trouble to happen before we take decision. So we need to be proactive. And how can you be proactive for what you don't know? You don't have idea about it. And if you can be proactive, for example, we can have an idea of when pests may likely strike. Then you can then prevent it. Start applying the necessary chemicals that can prevent it or interventionist system that can actually prevent the pest from causing havoc. You can just go to your bed and wake up tomorrow and the whole farm is full of pests. Before you do anything, it is too late. Can we have a kind of proactive decision-making process? This is why the need for predictive solution to improve towards improving agricultural production cannot be overemphasized. What of even harvesting? If we can have an insight of the best time to harvest our crop, that would be great. A little delay might lead to losing some crop yield, pest, and some other diseases that may also crop up because it has overripe or overready for harvesting. A host of others that we recommend for us to, again, visit our archive on our YouTube channel and see some of these discussions we've made in detail in the past several episodes on crop production. We said if you want to do that, you have to have the data collection, or the machine learning model building. You may have to use IoT sensor, remote sensing, and of course, the decision support system, where you can integrate the predictive models and the sensor data into decision support system that provide actionable insight for farmers. You tell farmers what to do and as at when. Yeah, it's good to have professional farmers. Everybody cannot be a professional farmer. Even professional farmers, sometimes they are not aware of what may happen tomorrow. They are human beings. However, with enough data set, with big data that is available now, and the capability or capacity of machine learning to effectively manage and model even data in motion. When we talk of big data, this is data set that is characterized by things like volume is huge and velocity is moving.
is changing, constantly changing. Because we don't want to miss any opportunity, we have to analyze the data even while the data is changing, which is one of the unique feature of machine learning. Statistical approach does not have the capability to model data that is in motion. But with the coming of machine learning, this has become very possible. That while the data is in motion, it is also being modeled. And that is the big game-changing capability that machine learning brought into data science. And that is why today people are getting confused. Some people thought that data science and machine learning are the same thing. No, they are not the same thing. That will be another discussion for another day, inshallah, where we're going to look into data science. Machine learning is not data science, or data science is not machine learning. So we'll be able to tell us what is data science and what are the capacity and the limitation. Before the coming of machine learning, data science were being done using statistical methods like SPSS, ARIMA, and a lot of other statistical is also one of them, and also for those people who used to do data analysis before. However, they are limited in their capacity to predict with precision, and also they lack that capacity or capability to handle data that is in motion. Statistical method needs that we froze the data or the data is frozen before you can use the statistical analysis on them. Again, like I said, we're going to come back to this one later and then see. Now, so if we are able to implement carefully selected predictive solution for crop production, our expectation is that farmers can experience significant increase in crop yields due to more informed decision making, resource utilization also. They can be able to make use of the available resources like water, pesticide, with the hindsight of a carefully optimized decision making, thereby resulting in cost savings and environmental benefits. Sometimes you don't need pesticide. If you don't need it, there's no need to use it. You're wasting money and also putting the environment into jeopardy. So if our data-driven decision-making says, no, there's no need for pesticide now, then there's no need to do it, and there will not be any problem if the decision is carefully taken, which human being will not know. There are some things that human being thought that this has to be done. It's a routine because that's what we know. However, data-driven decision-making is changing the whole thing now because farmers can have an idea of when there could be outbreak of pests, where could be consequence if we don't use pesticide. If there's not going to be consequence, then there's no need to use it. So with data-driven decision-making, a lot of losses can be prevented. And of course, improve sustainability practices and reduce environmental impact through what we call precision-oriented resource management. All this we discussed. Then we also look into practical demonstrations in Weka environment, which we highly recommend for every one of us to install Weka. It's very simple to use. We decided on this. For those who already knew how to use Python or R or MATLAB, you are good to go. However, machine learning, AI, is different from programming. So you are not from programming background. You don't have to suffer yourself or run away. I've seen a lot of people who left learning machine learning because they struggle to understand machine learning. They struggle to understand Python or any programming language, but they couldn't cope easily. They left. You don't need to leave. With the no coding AI, you can actually build your model, deploy your model without writing a single code. That doesn't mean those who already learned Python, they are going to lose. No, you continue with your Python. That is fine. However, for those who are not from that background, who are struggling with it, and the good news, even people who know how to write program, you can still use no coding AI to do your work in a faster way. Because you may be struggling to debug a single line of code in programming language for weeks without success. However, with no coding AI, just click and get your result out. And nobody is going to ask you why you didn't use programming. Because what we want is we want to see the outcome of your modeling. And that is what is very important. So I love programming, but still, I sometimes I still work using no coding environment, depending on the kind of work I want to do and the time availability. So that is a good news for everyone that you are all on board. And that's why one of our principles is machine learning for all. Everybody can actually learn and practice how to use machine learning to solve problems in our various areas of interest. So we also delved into practical demonstration in Weka environment to see how we can use this principle to build our own model. And if you remember, we had a data set that we actually had. So we are going to again bring up that particular data and then see what practice we can make of it. There was a data on yield that we brought up. So the first thing you have to do in the practical demonstration of it is for us to go to the Weka environment. When you are in the Weka environment, you click the Explorer. You click the Explorer. When you have the Explorer open, how do we use Experimenter? If you check out our videos in the YouTube, you see a lot of the explanation of how we can use this. So we go to Explorer. Once you click that, it pop up for you, and then you can open the data set that you want to use. You click Open, and then you can go to the location of your data. Look out for where your data is located. So, and I want to believe we have our data somewhere here. Assume weekly classes. You can see, I think the data is here. However, because this thing is expecting ARFF data file, so it cannot locate it. My data is in CSV file. So you have to change this. You have to change it here from ARFF to CSV. Say you are looking for CSV data, and that is a file that you made it in Excel file. But when you want to save it, you save as CSV. So this is the easiest way for you to bring data into Weka environment. You can see on changing it to CSV, you can see there are two files there. We have crop yield Indian states. We have crop yield data. Let's pick this second one. It's simple. So, and then we can click, you can see here, you're in the Weka environment and the modeling is about to start. So once you open your data set, this is in the, we are working in the pre-process area. You can see this is the crop, cocoa, beans, oil, palm, fruit, rice, rubber. So these are the type of crop that is being planted. Precipitation, this is another attribute. The amount of rain, specific humidity. See, relative humidity, these are some of the weather conditions gathered over time. And then temperature over time. Then this is the yield. The yield, these are real life data in so year when a particular crop like cocoa was planted and the precipitation was a particular value and specific humidity was this, relative humidity was this, temperature was this was the yield that we got. It means then with the continuous weather monitoring and forecasting, then you can be able to see and have an idea of, okay, with what we are having now, this is likely going to be what we can expect from our yield this coming year. So this is the idea of the data set. So it depends on the kind of data you are gathering in your own farm. You may have other data set that is different from this. We call these features. These are called features. Crop is one of the features. Precipitation, specific humidity, another feature. Relative humidity, then temperature. But what we want to predict is yield, the amount of crop yield that we're expecting from that particular plant or from that particular yard for that season. And then when you bring in your data, already told us we have to make sure the data, the last column, which is yield, it should be on the rightmost column in your Excel, in your CSV file, because it automatically picks the rightmost column as the target variable to be predicted. You see, so we have to take note of this. However, that does not mean we cannot change it. If I didn't do that, I put it at the first one, then you have to manually indicate what you want to predict. And you go to classify. You can see here, you can see yield here. It has already selected yield automatically as the target variable to be predicted. If it is not the one I want to be predicted, maybe I want precipitation to be predicted, then I will select precipitation. This now, whenever you run a model now, you're actually predicting the amount of rain. If we are expecting this kind of yield, what is the amount of rain that we should supply of, amount of water we should provide for it? Or I want to do, that's what we call reverse engineering. We do it sometimes. We want to investigate, okay, if I have this kind of crop and I'm expecting a particular amount of yield, what is the humidity that I should provide for maybe you're having a special, this kind of planting, a control environment for your plant. So you want to do reverse engineering for it. If I want a particular amount of yield, what are the kind of attribute I should supply for it so we can investigate it? I want to know the amount of precipitation I should provide, or even the type of crop that I should plant if I want a particular type of yield or the amount of profit you are expected to have. However, because sometimes you may forget to do the right thing here by changing this is why we always say that the target variable, you make sure it is on the last column because it will pick the last column automatically. Now, once you are done with this, we also explain to ourselves you have to select how you are going to divide your data. The most popular one is what we call the percentage split. You split your data into two, training and testing. Usually we prefer to make like 70% for training and the remaining 30% is automatically for testing. See? So we can use crowd validation, we can use supply test, say this another one for another day. However, this, let's say we have 70%. Now it's time for you to select your algorithm that you want to use. You go in. I want to start with a simple algorithm, which is, we call it the lazy classifier. One of them is the IBK. So once you hover it, it will show you K nearest neighbor. This is one of the simplest algorithm we do use. It's like, show me your friend, I tell you the kind of person you are. So we click it. We are using K nearest neighbor. Then we want it to work on our data set. So we can say, okay, start. Start means work on our prediction. We can see that it's faster because the data is not very big. So now it's able to produce correlation coefficient of 0.9964, which is 99.64. The correlation, that is the predicted and the actual expected outcome, they are very close together in terms of correlation. While one is increasing, the other is also increasing because this is positive correlation. When you have negative correlation, that is not bad, that is bad for prediction. We have mean absolute error, we have root mean squared error, relative absolute error, and also for the performance measure that you can use. And people ask me, how do we know the performance measure to use? I say, okay, it depends on the performance measure that has been used in that area. So look into literature, check out the established performance measure that people do use, and then you can use it. However, if you are the first one to establish predictive solution in this area, then you have to come up with the one that is appropriate. Somebody may say, is it possible? Yes, it is possible. I have one of my former student that in his field of endeavor, he established, if I is the forerunner in using AI for predictive solution in that area. He practically came up with some of the performance measure that should be used. And as an advice, at least you should use not less than two. You cannot depend on only one performance measure. So I used to advise people, check your correlation coefficient, one. Root mean squared error, also very good. You see, at least two. Root mean squared error and correlation coefficient. If you have to use only two. Then if you add more, it's better. If you are the first one, you are the forerunner in that area, at least use two to be able to see. Because this root mean square error will give the opportunity to see the direct error between prediction and the actual. So this is a first run for you. And now I can see the actual prediction. If I want to, you go to more option, go inside here. You see output prediction. I want to see the actual prediction. You go here, here it is null. It means by default, it doesn't show the predicted values. You want to see it, you choose how you want it. You can choose a CSV file. It will write it to a CSV file in this folder in your computer. It could show in HTML. To make it faster for us to see, I want plain text. See, I want to see it just like I'm looking at the performance measure. Plain text. Okay, it goes. If I run the same, you can see here, I can't see anything. Then run it again. Then you can see your predicted outcome. You see, this is the instance. And note that what you are seeing here is 30%. The testing set is what you are seeing. If you want to see for training, you have to go back and say, show me output model for training. Usually it doesn't show it because the screen is going to be too full. But if you need it, you can say, show me output model for training. Then it will show you for training, because training is not what we are looking for. What we are looking for is the testing, which is the most important. So these are the actual value provided in the CSV file provided for our system. This is what our KNN predicted. Here it was 151,070. He predicted it to be 150,428. This one is 5,903. This one is 6,002. You can see here, you see the error, the difference between the prediction and the output. You can see there, you can see physically how your prediction is working. How is it faring? If I'm you, I usually ask people to copy this. You can copy this entire stuff and take it to Excel. You can take it to Excel and then plot it out, and then you can see how close they are. You plot the actual and the predicted on the same plot. And you can see, are they touching each other and how far are they away from each other? This is how you can determine if your prediction is actually good or not. And of course, so sometimes when you have your prediction outcome in 099, it's just buried in number. People want to see visual analysis of it. Let us see exactly how it is faring. Are they close together or not? This is when you need this kind of thing. Just export it to Excel, make very nice plots, and then your report is ready to go. If you're a researcher, you are ready to push your work to the outside world to see what you have done in this area of try to use machine learning for crop production improvement. This is just an example, and we have only done it for one algorithm, which is k-nearest neighbor. And even that for that algorithm, we still need to go back again and do what we call hyperparameter optimization. This is the default value. K is equal to 1. We need to change the value of K and also change the value of, if you can search for our YouTube channel on k-nearest neighbor, you see some of the description we provided earlier on how to use k-nearest neighbor. The k-nearest KNN, which is the number of K, number of neighbor to be used, is the hyperparameter. There are two hyperparameters here, the number of K and also the, what do we call it? The distance measure. What is the distance function you want to use? We are using Euclidean distance by default. There are other distance measure you can use. It could be shape distance. It could be Manhattan distance. It could be Minkowski distance. The mathematician knows better. And we can also come up with our own distance measure that if you think is better than others, all those ones. Then you select one. Euclidean distance is the default value, so which we're using. You keep the default Euclidean distance, and you keep changing K. From K, change it to 3, and then run the experiment. See, maybe you get better result or you get bad result. It increased from 996 to 9974. So it's getting better as I increase the number of K, make it equal to 7. At a point, it goes down. See, at a point.
Can you hear again, sir?
At a point, it may go down. Please, can somebody type? I don't know what that man was trying to say. Can you still hear me, please? Can you chat with me? I hope you can still hear me and you can see my screen. Okay, thank you very much. Thank you very much. So, thank you very much. We are going to be calling today soon so that we can have time for question and clarification for whatever may not be clear. So, as you go in, you keep changing the value of this is what we call hyperparameter optimization. You run it again. It has gone down. From 997 now, it became 9967. It means the best K you could maybe possibly have, maybe is 6. The one that gave you the best before it started going down. Then you go back to here. So you put the good value here, maybe 5. That gave us a very nice result. Let me see. What is 5 given? 996. No, it seems we got the best from 4. Maybe 4. We have to check. 9974. Yeah. This is the one that gave us the best. So we're going to stop at 4. Now, the best value of K is 4 for this data. Now we move in and try to check. Let's check Minkowski distance. Are we going to get the same result or it takes us back? Minkowski takes us a little bit. The same thing. It's not changing. Yeah. So the same value is still there. So we go to Manhattan distance. Run. 98. You can see it's brought it down. So you keep checking that what you are doing is you are doing hyperparameter optimization. It means we can just assume that, okay, it seems the Euclidean distance is giving us the best for this data set. And then we can conclude that, okay, for this, we are stopping at this. Get all your parameter here, get the predicted outcome, start writing your report. It's always good to try another algorithm, at least 2. So we may also want to try decision tree. You go to the tree family. We have decision tree there. So random forest, no, we are not going for that. Try a simple decision tree. And then you can start also running that. That's also give you run 9951. So this is the output also that is providing. Then we can compare the result. Because in machine learning modeling, we do more comparison. We want to see which method is working better for you. But once you get 1 or 2 methods that are doing fine, you pick the best among them and you can move on. If someone has done it in literature, but you were able to get like 90% or 95%, that means you still have opportunity to come in and improve upon their work. You see, that could be your motive or motivation. You want to improve upon what they have done. So you keep going back and forth, try to improve what you have gotten. This is a procedure we can actually utilize in our various areas of specialization. And like I said, it's good for us to follow us on our YouTube channel and see some of the videos we've uploaded there that can benefit us. This is just kind of more of revision for what we have done. So because people have been away for a long time due to the break, and hopefully we bring out back now afresh to refresh our memory. The principle of iterative processing is what we are going to be using, and it's very important. So what I was discussing was we did the first model, we uploaded the data, we did the first modeling using KNN, we checked the performance, it was not good enough, so we go back and do hyperparameter optimization. You keep going back until you cannot improve it any further. Then we change the algorithm to decision tree. You do that again. So luckily we are getting something reasonable. 99% accuracy in the correlation is super rich, super excellent. Sometimes you are stuck with 64%. You have to keep trying different algorithms to see how you can make it better. Sometimes you have to do what we call the mixture of different algorithms if the data is really tough. See, in some competition, they give you data that is really, really tough. There's no amount of algorithm manipulation you do, it will never work until you come and add several algorithms together in what we call ensemble. Then you may get something reasonable in the competition. Most of the competition always, the best, the winning team always use mixture of many algorithms, which we touched it already in some of our videos as we move forward. So thank you very much for listening. We are going to stop at this point to give room for any comment or question or clarification before we call it a day. So I wish you all the best. Thank you very much. And I believe, yeah, this is time to have few questions. And then we'll come back again another day by the grace of God to see what hopefully we can have for ourselves. Thank you.